first of all, I have to tell you that the topic itself is like some sort of a clickbait for the tech talk because of basically of two reasons. First thing is I believe that going straight to implementing TensorFlow in React would be wouldn't be that much useful if if the general audience doesn't have an idea on what is TensorFlow and what is machine learning is. And the other thing is with the availability of TensorFlow, implementing machine learning on React has become so simple that it's like only take few lines of codes to do that, and it means it would end the presentation in a few minutes as well. So I may have to take a bit of a detour to set up the environment to make things clear a bit. So I'll start with what is machine learning. So I don't think there's anyone who's not familiar with this buzzword because it's like one of the most famous tech terms that we are using nowadays. So since the object of my tech talk is to make the general audience more fascinated by machine learning, I'll try to keep this simple as possible. Where it is very common to see that people who are familiar with machine learning find it very interesting and simple, while on the other hand, people who are not familiar thinks that is really complex and difficult to get used into. It is true that it's complex, but that does not mean we can't practically use it, which means we can basically, with the available libraries and functionalities, we can try machine learning, practical applications of machine learning very easily and very easily. So machine learning is basically the field of computer algorithms where the algorithms are learned by themselves. So in other cases, we have algorithms. We code the methods or functions, then they do some sort of task. That's the end of the story. But when it comes to machine learning, we don't usually implement them on simpler tasks. So at each time the code runs, the algorithm train itself, it gets better at its job. This is basically happens because we continuously feed data into machine learning algorithms, and also these machine learning algorithms learn by their experience as well. Now let me go to another buzzword, the neural networks. So before explaining what is neural network, let's take a look into the hierarchy of how these how these things are actually arranged. So on the machine learning is a subcategory of artificial learning. So artificial learning simply means where we try to mimic how humans think, human thinking pattern through the computers. So as a subcategory within artificial intelligence, we have machine learning. And deep learning is a subcategory of machine learning. So neural networks belong to deep learning. The reason why I am focusing on neural network is because TensorFlow is heavily focused on neural networks. So when I take a classical machine learning algorithm and a neural network, the main difference between those two, the fundamental difference is in a neural network, there are layers. In a classical machine learning algorithm, we know how the algorithm works. We know which parameters get trained or get tweaked after training them. It is just straightforward. It's kind of straightforward when compared to neural networks. Neural networks, on the other hand, are based on layers of networks. And when we input some sort of data, these layers would trigger trigger the layers next to them, causing a chain reaction, which would ultimately produce the result we want. So, coming to the idea behind a neural network, the concept got its motivation from how neurons work in our brain. So as you know, when we think of doing something like moving lifting a finger, what happens in our brain is we trigger some neuron cells. Then these neuron cells would trigger another set of neuron cells, and so on. They will create the chain reaction that I mentioned earlier until we get our task done. So that's the same. Neural networks are also motivated by the same principle. So if I draw the simplest form of a neural network to explain, it could look like something like this. So basically, each neural network would have an input layer and an output layer. Input layer is the part where we input our data. And between the input layer and the output layer, there are multiple hidden layers, and the number of hidden layers are not fixed, and there is no definite way to say that for this neural network there must be this much of hidden layers like that. So and in each layer there are nodes, and these nodes are connected to the other nodes in the preceding layer. To put it simply, we can say the nodes and a certain layer can be like roughly matched to a index and an array and array index. So likewise, we have layers, and in layers there are nodes. These nodes are connected to the nodes from its preceding layer. So when we input something, a node, a certain node would trigger some other nodes corresponding to its preceding layer, and so on. This triggering would keep happen. However, even other than this simpler explanation, there are concepts like activation functions, weights, which are involved when how mathematically a neural network is working. But I won't go deep into them because it would lose the interest to many of the audience. However, even though this is the simplest way that I can represent it, I need to show you this diagram because at least when a real neural network is implemented, the complexity between and the connection between neural layers and nodes would be it would be even greater than the image shown here. So I hope this would provide some idea about the complexity of a neural network. So to further, and there's this thing when it comes to when it comes to a classical machine learning algorithm. Since we know how the algorithm works, we can figure it out in our mind how the result is produced once we once we execute a classical machine learning algorithm. But it is a bit difficult when it comes to neural networks. So let me take like the simplest example I can think to explain how all the factors get combined and work in a neural network to produce a result. So here's a neural network, basic structure of a neural network, which is created to recognize handwritten digits. So recognizing handwritten digits is like the hello world when it comes to neural network, hello world program. Uh, let's say we have only two hidden layers between our input layer and the output layer. Also, please forget this number 784. So what we give as the input to our neural network layer are the images of our handwritten digits. And let's say these handwritten digits are of fixed size, something like 50 by 50 pixels. Then it would means each image would have 250 pixels in them. And if these images are of grayscale type, then that would mean each pixel would have a value between 0 and 1. So you can think when we are saying we are inputting data to the neural network, what we give as input is this value of each pixel in our handwritten digit image, which means we would have 250 nodes if the size of our input image is 50 by 50. Then at our input layer, there would be 250 nodes. Each node would correspond into a specific color pixel. So now we have that data at our input. So in the end, what we want to do is recognize which number is this. So the magic happens in the hidden layers. So to understand roughly how this happens is, we can say each number, let's say 9, 8 or 4 or any number, we can say can be represented using circles and straight lines. So if you think it like that, a 9 would be as you can see in the bottom image, a 9 would be a circle and a straight line, while an 8 would be two circles located like that, and a 4 would be three straight lines, likewise that. So if we can figure it out, this pattern in a certain layer, then we should be able to deduce which number do we have. Now, then comes the question: how do we recognize if if the shape is a circle or a straight line? To that, we can say what happens is something like in the top image. Even a circle can be decomposed into several parts and several minor parts, as in the top image. And straight line also can be divided into smaller parts like that. So in our previous neural network, we can say if we have two neural hidden layers, in the first hidden layer, what happens is the nodes in the second hidden layer are corresponding to the features that is represents the parts of circles and straight lines. So when I give the input of the color input as the value of pixels, each pixel as input, the nodes corresponding to this input should trigger the corresponding matching pairs of basic shapes in the second layer. After that, once we have the basic shapes, then the nodes corresponding to those shapes should trigger the nodes corresponding to the circles and straight lines in the third layer. So that's how roughly that's what happens in a neural network. And after the second layer, then it should trigger the output node corresponding to the number 9. So we can this is like the simplest way I can explain neural network to you. And this is get really complicated because there would be many more hidden layers than that. But basically, what happens in a neural network is something like this. So then now, since we have some sort of background knowledge on neural networks, then we should come to coding our first neural network. So as you saw earlier, it was a bit hard for me to explain how a neural network works, how a neural network works. So coding a neural network from scratch is really complex. So that's where TensorFlow comes in. So TensorFlow is a free and open source library. It was developed by Google in 2015. This TensorFlow is basically focused on training neural networks. So the TensorFlow works on the concept of tensors, and I would explain what are tensors in the next slide. And the other key special thing about this is it uses GPU when it comes to training neural networks. Unless you want to spend like a day to train your first neural network on your CPU, using GPU is the most reasonable and time-saving solution when it comes to training neural networks. So what does TensorFlow fill is it fills the gap the complexity between creating a neural network from scratch to the general audience where they are interested in doing practical applications of neural networks instead of worrying about how the mechanics of a neural network and how the inner components work. So as I told you earlier, I told you that TensorFlow is based on tensors. So this gets some people confused. That's why I decided to include this slide. So a tensor is basically a array of some dimension. It could be a one-dimensional array. It could be a scalar. It could be a matrix or a three-dimensional array. But in the end, it's just an array. That's the name that the Google developers came up with. And basically, what TensorFlow does, it deals with heavy computations related to matrix manipulation in the most efficient way. So before creating the first neural network, there are always basic steps when it comes to few basic steps when it comes to creating any neural network. First, we need to have a data set. If we are doing supervised learning, most of the time we are doing that. We need a validation data set and training data set. I'll get that to in my demonstration. Then there's pre-processing of data. The pre-processing part is like it's like a complete another topic for a tech talk. But so that I would go only I will only scratch the surface of it. Then afterwards, we need to create the model. Here we will be using the TensorFlow. Then we will train and compile the model. Afterwards, it's just like using a component, like using an inbuilt function. Once we have the model, all we need to do is use it. Then to start creating your neural network, what do you need? So you would probably need some sort of programming language. I would try to recommend Python because it's like the easiest language to handle, to get familiar, and there are a lot of machine learning libraries for Python as well. Then an IDE or a distribution platform. Then also, then you are going to need NVIDIA CUDA toolkit, unless you are planning to create a neural network on a CPU. And of course, if you are planning to use the CUDA toolkit, you need to have a better GPU. And there are many manual installation of other libraries as well. And trust me when I say this, if you try this by yourself, it would at least take a couple of hours, and it would waste like 2 or 3 GB of your data. And the possibility of you end up if you're getting fed up with learning neural networks is very high. So if you are starting new, I would really suggest the data science community Kaggle. So let me get back. Let me get to my first demonstration part. I hope you guys can see my screen. So this is Kaggle. Kaggle is a data science community. The thing about Kaggle is it's the notebook that Kaggle provides. So basically, Kaggle provides all the latest machine learning techniques, machine learning libraries, including GPU performance as well. So here it's free and you can register there. Once you register, you can come into this code section, and here you can see the work that I have been doing. So this is the notebook that I created for to show you how to do a basic neural network using TensorFlow. Another thing about the notebook is, if you are not familiar, as you can see, there are separate cells, and we can add more cells using here. And these we can run each of these cells separately. And once we execute them, the data we do execute here would be stored until the session is over. So another thing to notice is I have set the accelerator option to none. I will get back to this in a while. This example is the typical example provided in the TensorFlow website for image classification. So this includes a fair bit of theoretical stuff as well, but I'll go over them and explain only the basic stuff to keep to stop this don't make you get bored with this. So basically, at first we do basic imports. Matplotlib is a Python library that where we can use to draw images. PIL is also a library that where we can do stuff with images. Here's the big guy, the TensorFlow. NumPy, basically we use it to handle arrays. Keras is a platform just like TensorFlow, but it is for machine learning and neural networks on Python. And sequential is the architecture of the model that we would be building here. So to run this part, all I need to do is execute this segment, and it should get executed fairly quickly. Yeah, that's done. Afterwards, what we are doing is we need, as I mentioned in my previous slide, we need our data set. Here, the part what we are doing is we are getting our data set. So once that is done, you can do some tweaks and like get how many images we have in our data set. Like here it says we have 3,000, some sort of 3,000, and here using PIL, you can see what sort of get a quick look at what sort of images we have. If we enter another number, we can see a different flower. So now here comes another part, another important part. This is where we create our data sets for training and validation. So here the batch size, what batch size referring is, when we train a neural network, it happens in iteration. So batch size is how many samples we would process at each iteration. So here we say 32. So we would process 32 image at a single iteration before we tweak our neural network model. And as you can see, we have already given a fixed image height and width. This is because all the images should be of fixed resolution when we enter them as input to our neural network. And here is a basic syntax to create the training data set. This even I don't know the deeper meaning of this validation split and say it like that. But the other stuff are basically self. You can understand it when you see the syntax. So here we are creating the training data set and the validation data sets. Now, once that is done, we can here we can see the class names, which means the categories of classification we are doing. So we are classifying flowers into these 5 categories. This is actually this is not related to machine learning. What this part does is it shows an array stack of images, so we can look into a set of images at once rather than looking at images one by one. Then another important part is here you can see that we are doing some sort of a shuffle before we we create the model. This is the part where that I mentioned as data pre-processing, because we are doing this to make sure that we get the highest accuracy and to prevent overfitting of the model. So the overfitting of the model refers when we train a model on a specific data set, the model get used to that data set and it would give very good result for that certain data set. But when we move to a new data set, we don't get better result as we want. So after that, we have this normalization concept. What we are doing here is, since we are processing images in our neural network, usual JPEG image has for 3 channels to RGB colors, and each channel would have each pixel in each channel would have a value between 0 and 255. So it's always when we are creating neural networks, we don't keep a larger value like this. So we always try to normalize them to a value between 0 and 1. So what we are doing is we are mapping all those channels to a value between 0 and 1 before letting them as sending them as input to our neural network. Now here's the moment of truth where we create the machine learning model. As you can see, with the help of TensorFlow, creating a neural network is only a matter of adding new layers and doing the max pooling and again adding new layers. And yeah, these few lines of code would take like hundreds of lines of codes if we were to do it from scratch. So let's do that, and again let's do that as well. And afterwards we can compile our model. This syntax gives a summary of our model, which does not we don't need to look into that because we are not going to technical stuff. Now here we are coming to an interesting step. Now what we are doing is we are going to train our model. So here, as I said, I didn't use my GPU, the GPU they are provided by Kaggle. So you can see the way it goes is it's fast, but it does not it is fast as we want, because this need to happen 10 times, and at this rate we won't get completed it within like 5 minutes or so. So here's what we can do a trick. So instead of using our CPU, we can use this GPU option, and we can turn on our GPU. So once that is done, our session would restart, which means we have to wait a little bit. And okay, our session is started. Okay, now I'm going to run the steps that I executed earlier. First step is done. Let's do the importing part. It also done. We don't need this. Let's create the training dataset and the validation dataset. Now we create the class names and do the pre-processing. Also the normalization. And here let's create the model, compile it. And now we are training the model using the GPU, and you will see how fast it is when we are using the GPU. Now you can see that this would get finished really quickly, and this won't happen if we use the CPU. And why I suggest Kaggle is we won't get this speed even if we use the GPU in a normal ordinary laptop. So afterwards, this is the last important part where we use our model. So in this whole piece of code, the most important part is this model.predict1. Now we have our model. All we need to do is this is all related to getting this image array where we need to test our data. So we are getting a sunflower, and we are feeding it to our neural network. And as you can see, we are getting this 99 our model predicts that it belongs to a sunflower with this much of confidence. And there are some other concepts of which includes fine tuning this, so we can go to a better accuracy and to avoid overfitting of the model as well. I would skip over them because they are like a bit of heavy on theory side. So that's pretty much it when it comes to creating a neural network using TensorFlow. So with use of Kaggle, or you can use Google Colab, but the specialty of Kaggle is since it's a data science community, there are a lot of pre-trained models and data sets available, which is not the case for Google Colab. So with those two, you can pretty much start creating your own neural networks from scratch. Then coming.
Excuse me, Isuru.
Yeah.
Is Kaggle freely available?
Yeah. Kaggle is
even with the GPU selection.
Yeah, there are limitations, however, which means for the GPU, we only get 30 minutes on training time. So obviously, we have to move to another money-based thing if we need to get more GPU time.
Okay, so why I asked, so I can remember even to run some CUDA codes, you need to have several types of GPUs, the supported GPUs. So probably this will support this.
Yeah.
Those kind of GPUs. Okay, cool. Thanks.
So coming back to my presentation, since so where were we? Now I gave a little bit of a background understanding on what is TensorFlow is. Now let's come to the hot topic for today, the TensorFlow.js. So here is where things get interesting. So in 2015, TensorFlow came, and 2018 they released TensorFlow.js, which is a JavaScript library. So this is specially designed for browser use and Android devices. The thing about this is it takes a lot of computational power when it comes to training neural networks. So what this TensorFlow.js is really heavily optimized for its speed to get the most out of what we have in our machines, and also it allows load the existing model into our browser. So we don't need to waste time on time training models. So simply we can integrate TensorFlow into our web app using TensorFlow.js. So, and it can be used on React Native, React JS, Angular, basically on those things. So that's what. That is what I think the most important thing about TensorFlow, because to us, because with the TensorFlow.js comes this commercial value, because unlike doing simple neural network stuff on our PC, once we have TensorFlow.js, we can add specific machine learning and neural network widgets to our web apps as well. So the advantages is one concern in the community when creating commercial applications using machine learning is that we need to store the customer data, because it basically machine learning models get trained through the data we collect. So there's this privacy issue. But through TensorFlow.js, we can do the training on the browser itself. So we don't have to train anything. We don't have to store anything at our end. And the other thing is we can create customized machine learning models for our customers using TensorFlow.js. So instead of using a single model at each end, we can create a separate model. Then it is also the fact there's the advantage. It is very easy to integrate, and you will actually get amazed how it easy to use TensorFlow.js on React, because it just like using another component available in React. So coming to my demonstration on React TensorFlow.js on React, I have two demonstrations ready. First, let's get to this image classification one. I already did some coding to save time, because I don't think I need to waste time on the basic stuff doing here. So what this app do is I have a set of images of these animals in my this repository. So I'm importing those images, and I have this image component where I send these images. And in my image component, what I have is when it comes to render, I have a label, a bit of a user interface where UI, where I have this label, and the image, I display the image, and a button to do the classification, and also this display text displays the status of what we are looking at. Wasting further time, let's get to the interesting stuff. So as you can see, when I click this button, classify image, it triggers this function. It's an async one, because there are a lot of asynchronous calls going here and there. So first what we need to do is make sure that TensorFlow is ready to use. So we do that by this basic command. And afterwards, we need to load our model. So for this, I'm using this model called MobileNet, which is specified to detect, classify images, classify animal images. So I need to load the model. So how I do that is basically I create a class, let's say net, and await mobile dot load. Okay, that's done. Then we need to fetch the image. So to fetch our image, let's create resource. Wait, have fetch. We can simply give our state this state dot my URL. Now we have our image. So now what we need to do is we need to uh, put create a buffer from our image, integer buffer, byte buffer. To do that, const image. Let's say it's image data plus wait, uh, resource dot array buffer. Okay, now afterwards, now the thing is this actually different from the model, differs from model the model we are using. In our the model we are using, the MobileNet one, it accept tensors as input. So we need to convert our image data to a set of tensors. So let's say we have so that's why we have this function image to tensor. So let's call that function here. Let's say we get image tensor. After I call this function, this dot image to tensor. Okay, now I sent my image data to this image to tensor. So here what we are going to do is first we going to first we are going to extract the binary data from our image. To do that, I am using const width and I need height and let's say data. To extract the data, we are using the model component JPEG. JPEG dot decode. We supply our raw data we got as input, and then we create the buffer of binary buffer. So the size of this buffer would be width of the images by height times 3. This is because for each JPEG image, we need 3 channels of colors or RGB. And I'm doing a little trick here. Let's say I'm creating this offset and setting it to 0. I'll explain why I'm doing this in a bit. Now I'm creating a for loop. So let's say I equals 0, I less than buffer length. I am getting it. Okay. After that, buffer height position of the buffer to data offset. let's copy paste this 2 more times. Here it becomes I plus 1 for this one is for red channel, and now it's the green channel, and now for the blue channel. Now let me come to the point why I create this offset parameter. The reason is for an JPEG image, there's a fourth channel which is the alpha channel. We don't need that, so I'm using this offset to bypass that. So now we have our image to tensor function. Now we can get the result because now we have our tensor. We need to return the tensor. Return ts dot tensor 3D because we have a 3D tensor. So we give the buffer as input and the dimensions. The dimensions are height, width, and 3. So this gives us our buffer. This gives us our tensor. Now let's get our result. To get the result, let's say const prediction is await. Now we are using the net that we created in the beginning, and let's put the image tensor to that our neural network. So that's it. These are the basic steps if we are using if we are using a pre-trained model. So let's say I'm converting the prediction into a JSON format so we can see it in our user interface. And we would need a few packages to do this. Those are these are the ones that we are need for this specific application. Of course, you can add them and just run npm install, or you can, if you are not sure about the version that you want to use and want to get the latest version, each of these can be separately installed using the npm. Okay, that's done as well. Okay, now let's fingers crossed and hope this works. Start. So it takes some time to launch. Okay, now we have it. I have this squirrel image. So if I click the classify image, it says we can see at which step we are there. So it classified this as a fox squirrel. I'm doing this in a very rough manner. So if I want to say let's use shark, what I'm doing is one of the most, I don't think this is the proper way, but save time. So I'm saving it like this. And for Shark, I'm again loading the same same neural network. So the other thing is I don't need to call this again and again, load the model again and again. If we need to optimize this, we can load this one and use it again and again on this image as well. So as likewise. For all these animals, we can run this classification, and this happens at the browser level. But we are using a pre-trained model for this. Now, it had some little bit of lines to do, work to do when it comes to inserting the model. There's for my final demonstration, I would like to show something very kind of entertaining. And includes very few lines of codes. With the use of TensorFlow, we can do real-time object detection on the browser level as well. So for that we are using the Coco SSD dataset. Like in the similar way, like previously in store. And while that is running, let's close this. And while that is also getting run, I want to show you that TensorFlow.js web page as well. Here you can see the models. There are lots of models already available in the site as well. And there are some community developed models as well. So basically, if you want to start, you won't need to create a neural network. But probably there will be a model that suits your application. So object detection here is done. So in this, there's a fair bit of coding because I'm getting my webcam feed into the browser. So all this code is related to that task. So no need to pay attention to that one. I thought I erased this one, but it seems I have already done that as well. So here what we for the machine learning part, I mean to get the neural network up and running, what we need to do is once we have our video feed coming, all we need to do is make detections. So to do that, what I'm going to do is create this run Coco asynchronous function. So here we are loading our neural network. In this time, what we are loading is Coco SSD load, and we are setting it to execute at 10 millisecond interval. It's called detect, and we give the net, and time interval is now afterwards here I'm to do the detections, I'm calling the detect wait dot if you want to do some, if you are not do some add this to the console, because in case if some error pop up. So we have on it. Okay, seems like it's done, and it's this as well. So for this one, although there are a few lines of code involved to embed TensorFlow.js, what we need to do was implement this function and this line only. I have this one set up to do the to draw the box. You will see what's that in a minute. So let's run it and see if we can get it working. Yeah, it's running now. If we get to the console, okay, I was fearing this would happen because it seems while I'm on a video call, I can't use the webcam again. Oh no, it's working. I thought it would messed up. So as you can see now, it's do the detection in real time. So you can see that the bounding box is drawn around myself. So if I say show my phone, it would detect phone as well. It would take some sort of computational power to do this in the physical PC as well. So this is the advantage and the power of TensorFlow.js. You can see that it happens just on the browser level. That's it for the demonstration. Let's close this. So I have come to the end of my presentation. So if there are any questions, I would try my best to answer it. I'm not an expert on this, but I would like to help someone to get interested in this field if it is possible.
So, Isuru, have you done practical apps with this, like probably in your university also?
Practical, you mean using TensorFlow.js?
Yes.
No, actually, I was looking. I'm actually interested in this computer vision and machine learning aspect, and I was hoping to do the tech talk on that end. But I kept thinking on how it could be useful to GVO. So when I look into that, I saw that it can be embedded to the browser level as well. So that's why I look into that and thought it would be a good topic. So I haven't made any practical labs using TensorFlow.js, but on the PC level, I have done some.
Isuru, if we load up that web page on a phone, will the computation power will be enough for a smartphone to run the real-time detection?
It actually the TensorFlow.js is specifically made to use on React Native, so it's I think it won't have that much of a decrease in computational power, because I think it is optimized on that level. So basically, one of the main reason why TensorFlow.js there is to use the features of smartphones like the accelerometer data and stuff like that to make more interesting applications. So I don't think that would be a problem if we were to use it on a phone.
Yeah.